started. I'm Apurva and I am TA for this course, Games and Information. This is week 2 of the tutorial. Um, does anyone have any doubts in what we covered last time? Anyone? Alright. Um, so last time we started with very introductory things. We started with the definition of what a game is. Then we saw what is a solution concept that is typically considered. So the common one is Nash equilibrium, and we saw how to calculate it in simple games with very limited number of actions and very limited number of players. And then we saw that in certain games we might have a better scenario. We might be able to find strategies which are clearly better than the other ones, called as dominant strategies, and that allows us to easily say, just by rationality, by the assumption of rationality, that no player would play a strategy that is not the best one possible, or that's not as good as the other ones available. So that can just be eliminated from uh, the matrix, payoff matrix. Then we saw what happens if we have strictly dominated strategies and if we have weakly dominated strategies. We know that these were the main points of the theorems. We know that if we have strictly dominated strategies, and those are the ones that we are removing, if those are the ones that we are eliminating recursively or iteratively, then the Nash equilibria will not get created or will not vanish. So whatever is the Nash equilibria in the original game will still exist at the end of it. On the other hand, use if we were to eliminate weakly dominated strategies, one, the order matters, and hence we might end up with a different equilibria in different order of elimination, meaning the the equilibria can may not be present in the reduced game, but whatever equilibria we do see in the reduced game must be the ones that were there in the original game itself. These were the theorems and the ideas that we learned last time. Now, one of the things that we assumed here was that rationality is something that is known to everybody, that all the players are rational. This is known to everybody. This is more like common knowledge. And also we said that the game matrix is something that's known to everybody. Now this week is going to be mostly focused on the idea that things like common knowledge, or what does it even mean to know something, these are these are made formal under the Aumann model, and that's going to be the focus throughout. So today's tutorial would be slightly more abstract. I have a few examples in between, but it will still be a bit more abstract and formal than the last tutorial. Okay, so let's start. So this Aumann model of incomplete information, it says that there are some states of the world, there are some players that are in the game, and there are some the information is available to each of them based on their own partitionings, or meaning that, for example, a subset of y may be put together, and the that particular agent will not be able to tell the difference between the ones that are in the same subset or are in the same partition. And this kind of a partitioning is done for the whole y, and it is done in such a way that if you take union over for a given I, if you take the union over all the different partitions, so I'm writing it in an informal way, you would end up covering all of y. Okay, then what we have defined is an event. An event is nothing but a subset of y, or a subset of state of the world. So this was the key definition. We say that some player pi knows an event a in some state of the world w star if Fi of W star is a subset of A. This Fi of W star is an element of this curly Fi we had earlier. And we're basically focusing on the one which includes this W star. Okay, we'll come to an example first and then come back to these definitions one more time to be sure that there are no confusions left. So let's go back to the example that was described in class. That was of two players, John and Paul. One of them is colorblind and everyone knows that he's colorblind. The other player may be colorblind or may not be colorblind, but he's the only one who will know what is his state. They're both observing, say for example, a race, and they're just trying to find out who is the winner of that game and what is their information about what is happening there. So in such a case, if there are suppose 3 cars and 2 states for Paul, the state of John is known to everybody, so we don't have to worry about that. So it's only these state of Paul and car is what is used to define all the state of the world. So how many total state of the world are we going to have? I'm just asking the number, I'll write them down. So we have 2 states which are because of Paul and 3 because of these cars. So total number of states that we're going to get in this situation is going to be 6. So those are if Paul is colorblind and the car turns out to be purple. Similarly, all the other combinations. The other combinations are if he's not colorblind and car is any one of them. So whether it's purple or if it's green or if it's red. So these are the total 6 states. Now we had these partitions, right? All of these states are to be divided in some way depending on the way the problem is described. So let's do that for this example. What are the partitions for John? Okay, we can write. So for John, if the car that wins is purple, only then he knows. Otherwise, he can't distinguish whether it's red car or green car. And he has no clue whether Paul has won or Paul is colorblind or not colorblind. So these two will form one set. These will be one partition. So this is this is supposed to be in English. Will the others be okay if I mix up the languages? Okay, I'll try doing it this way. I'll say it in English and then I'll say it in Hindi wherever I can. Okay?
Just do whatever you are comfortable with.
Okay,
That's
yeah.
better.
But it's a request that we please be little slow.
Sure, that I can do. So for the time being, all I'm saying is these two together form one partition for John. This is okay. I think I'm going to stick with English. I will not be trying to switch languages in between. Okay, so this first point is saying that if the car that won is purple, John would know that purple has won because this is a color he can see. If he can see that color, he at least know, okay, this is the car that has won. Or he'll be like, okay, it is not purple. That's all he'll get to know. But at the same time, he'll not know what was the state of Paul. He'll not know whether Paul is colorblind or not colorblind. So for him, these two need to be clubbed together, which is why this forms as one partition and everything else will form as the other partition. So
Yeah. By the way, who is colorblind and who is not colorblind? You wrote like say Paul is colorblind and Paul is also not colorblind.
yeah, so what I'm saying here is John is definitely colorblind. This is something John knows and Paul knows. And John also knows that Paul knows. So you can say this is pretty much common knowledge. Okay?
Okay.
But Paul, if he's colorblind, only he knows. John doesn't know.
Oh, I see.
So
The problem is formulated like this.
yeah, the problem is formulated
Then,
exactly this way.
oh, I see. Right.
So
One
I
more
wrote it
doubt.
here.
Actually, it's very difficult to differentiate the common knowledge and the state of the world, which is you formed for Y. How are you forming that Y?
Right. So here I am saying state for John is fixed. He has no different state available. His state is that he is colorblind. Okay, so if I want, I can add that in the description of my state of the world. But because that is for everyone, I'm not considering it. Otherwise, I could have said that okay, the state of the world is written as each element of Y. Okay, so each element is written as what is John's state, then let's say what is Paul's state, and then finally, well, which car won at the end. That's another way of having defined what is the state of the world or all the possible states of the world. But because in this particular problem, John's state is something that we already know and it is fixed. You don't have to think of it as common knowledge, just think of it as something that is fixed. Because it is fixed, it's going to show up for everyone and it's going to show up the same. So I've just not considered it and I've written it only in terms of the things that might have some variations possible. So for Paul, there are two possibilities. Either he can be colorblind or he's not colorblind, but only he himself knows which one it is. John doesn't know that. And the color of the car is depending on which car wins. So that's something neither of them have any control over. That's an event that's something that's taking place on its own. Alright, so far we have written part of the partition for John. Now the remaining states, which is these two and these two, these four are going to be clubbed together for John. Okay, so that would be CBR. Can someone explain why that is? Why are these to be clubbed together?
Because then if someone is colorblind, then this red could be green or this green could be red.
Correct. He'll not be able to distinguish whether it's red or green. That's first point. Second, he doesn't know whether Paul is colorblind or not. So for him, those two are the same things. That's
But then I
why,
could not. But then I could not understand this notation which you wrote Y J or what I mean in the left hand side. So I mean on which criteria? I mean we are creating partitions here. For every player, are we creating partition
yeah,
or
partitions are for each player. They'll be different for each player.
so? If this is J and then where is for this Paul? Then I mean you have.
Yeah, I'm coming to that.
Actually, this notation thing is not that clear. Yeah.
I'm
So
coming to that. This is for John.
oh I see.
It's for each player because what is so it's like saying these two things can't be distinguished by me. For me, these two are the same thing. They may not have the same belief or the same interpretation by a different person. That's the kind of partition that we are doing. So it'll be different for each person. By chance, they may match, but in general, they'll be different. Okay, so far we have only said what is the partition for John. Now let's look at what should be the partition for Paul. Now that would be, so let's look at each one of them one by one. So for Paul, he would know whether he's colorblind or not colorblind. So there won't be any situation where both of these, for example, this or this, would be clubbed together, because he would know the difference between them. So we can start with this. These two get a split first of all. If purple car won, whether he's colorblind or not colorblind, he'll be able to tell it's the purple car that won. And he knows his own state. So these two are first of all separated. So if he's not colorblind, he can see it and he knows it. So this is one. This is another partition. Now we have already done it for purple. Now let's look at the scenario when he's not colorblind. When he's not colorblind, he can tell whether it's green or red. So again, these two would be separate. And they'll not be a part of any other partition either. So this would be NCB green. NCB red. The only ones remaining are when he is colorblind and he needs to distinguish between red and green. And colorblind means that that person cannot distinguish between these two colors. Meaning now these two should be in one partition. So these two should be clubbed, which says this would be the partition for Paul. Okay, so far what we have done is, given the description of the situation, we have just written out what are the state of the world, what is the whole set of the state of the world, which is Y, and then what are the partitions, or how is the information divided for each of them. That's all we have done. Okay, now the next set of questions that are possible here are dependent on what is an event, what is knowledge of an event, or what is the knowledge operator. So let's look at those two definitions one more time carefully, and then we'll try out those questions. So, right, is this part clear now? How the model is defined? Y refers to the state of the world, or all the state of nature, and
It's
this
okay,
is
it's
for
okay, but then lots of wisdom has been used while partitioning this entire space. Like, so the things are not mathematically grounded. Like I have used human wisdom to create the partitions. Like, okay, he's a colorblind,
see,
and since he cannot
you're
distinguish
you're
what is red and
given
green,
some
so in
rules.
that sense,
It's not random wisdom. You're given what the rules are of the situation, which is saying colorblind means that they can't distinguish red and green. There are other kinds of colorblind if we go by general wisdom. We're not talking about all of those. We're just saying this colorblind is red and green can't be distinguished.
yes,
So
yes.
it's just based on that. So the rules of the situation are already given. We're just writing out based on that. We have not used any extra information in writing at least this part.
Yes,
Yeah?
understood. Yeah.
Yeah. Okay. So let's move forward. Right. So next thing is, an event is just a subset of Y. So an event will just be a set of some of the state of the world, maybe not all. It could be all, but in general it will be something smaller than that. So we say whether an event occurred or not. Another word for occurred, which is going to be used in this particular context more often, is going to be obtain if the true state of the world is, suppose, some W star, if that particular W star is a part of A. So an event occurs when the true state of the world is a part of it. Okay, this is just how we're talking about it. This is more like the terminology or definitions. And we say a player pi knows an event in some state w star if the partitioning, the element of that partitioning, fi of w star, is a subset of a. This is the definition, and we'll see how it is being used. And this, if we use this definition, coming. I'll give an example to explain these words a little more carefully. If we look at all those w's which are such that fi of w is a subset of a given event a, then we say that is the knowledge operator ki of that event a. Okay. Okay, so let's take the questions. Okay, so remember in class, one of the things sir said was, suppose, let's say, the actual state of the world is not going to be all six of them, it's going to be just one thing. So for example, Paul is colorblind, so the actual one is, say, this one, and the car that won in the one instance that it happened is the red one. So in that sense, true state, or more like, you ran the experiment, this is kind of an experiment, some situation is occurring, and in that occurrence, what is the result that you actually had? So here, let's say it is cb comma r. So an event has to be something where this w star is included, and this w star is, in this particular case, here. If we were to highlight them in the partitions, it's here, cbr and cbr.
Is this CBR we are assuming or it is given?
It's an assumption. See, the true state can be any of these six. It can be anything. To move forward, if we want to, based on what we saw, if we want to decide how to take the next step, how to take the next action, we have to have a true state, which we may not know, but we are just trying to see if the players can figure out what is the true state, or with what probability they can figure out, depending on if they have beliefs and so on in this system. So there has to be something where it all started from. So that is just the only thing that is referred to as the true state. So if you're talking about an event and you're saying that event occurred, that means the true state is a part of that event. It might be there are a few more possibilities that happened at the same time. Is that clear?
Yeah, okay.
All right. So next, let's try and understand this knowledge operator. So this knowledge operator is, now notice how it's defined. The knowledge operator is defined as something that is acting on a particular event. So we need to know which particular state of the world, the set of state of the world that we are considering together. So that's our event A, and it is for the particular player. So the knowledge operator may act differently on the same event, but for different players, because they have different information. So this could very well happen, and we'll see how that happens in examples for this particular example. Yeah, was that a question, Dinesh? Okay, so then I'll move forward. Right. Now this part is important. Whatever we get, so suppose we are choosing a particular w. This is maybe I can draw a small diagram to make this point. Let's say the partitions are something like this. Okay, and I'm saying the event is just a subset of this. So this is like y, and this is the partition, and I'm saying this partition is for some player p. This is only for one player. For the other player, the partition might be slightly different. So I'm saying, okay, let's say there is some event that is happening, which is this orange region. This is what I'm calling as an event. So this is an event A. This whole, the divisions I've made inside these are referred to as the partitions for that one particular agent or player. So now let's say we're talking about one point. So let's say that point is here. So fi of w refers to that particular partition which contains this w. So in this particular example, it refers to this particular region. So what this above definition is saying, if that w, if this particular object is a subset of A, either it's equal to A or a strict subset of A, then that W is something that's going to be included in the knowledge operator. If not, for example, look at this region. Look at this W1. The partitioning for the ith player for this W1 is something that is not a subset of A. Since that's not a subset of A, that means W1 is not going to be a part of Ki of A. Here, this W is going to be a part of Ki of A. So this diagrammatically represents what we are referring to as this knowledge operator. So for a particular event, for example, this event A, Ki of A refers to this whole section, all the W's included in this section. Which are one partition, which can't be distinguished by that agent, but they're one partition, one element of the partition. Any other element, something here, or here, or here, or here, or here, none of that will get included in the knowledge operator. Okay. Now this is just for one player. So we could draw what would be the situation for the other player in the same diagram. Let me see. Hopefully this color will be visible. Let's say the partition for the other one is this way. Just something else. So in this case, this region forms Kj of A, where whatever I've drawn with green, these greens are the partitions for some other player J. Event is the same. So the point is, the knowledge of a particular event can be different if we are talking about different players. They could match, they could be completely different. They could at max overlap all of A, but typically there'll be a subset of A because that's part of the definition itself. Alright, I guess no further questions here. So let's take an example. Diagrammatically, it's easier to do, but if there's an example we have to work out, then it's a bit more work. So let's take a simple event for the time being. Let's say the event is okay, let's say the event is just this CBR. Then what can I say about the knowledge operator acting on this E for John? What will this be? Okay, see what we have to do. We have to look at where is this element. This element is over here. This is the partition of this element. Is this partition a subset of E? In this example, it's not. That means this is not going to be included in this. And we can't consider this partition because this does not include our event at all. So there's no point. That's not what we want to know. We want to focus on knowing the event. So here it is phi.
But then the CV comma R is a part of the partition for John, isn't it?
It is. But look at this. We needed this case, right? For John, for E. Not E, but let me just write it as CB comma R.
And what this F here is?
The partition. This, the element of the partition, let's say. So this, okay, let me write this as element. So F of J is any of the elements of this F of J. And similarly, F of P would be any element of F of P.
Oh, I see.
So now this thing is actually bigger than the event. I can
Yes.
take anything from this particular element, but the whole thing, this whole element is overall bigger than the event itself, which is why this definition is not satisfied. We needed all those states of the world W's for which Fi of W was a subset or at best equal to A. That's not the scenario here.
So, but then this CB comma R is a subset. Where is the issue? What is not the subset? This CB comma R
We are
is one
not
of
looking
the
at just CB comma R. We are looking, see, in this diagram, I was not just looking at that point. I was not looking at just this point. I was looking at the partition because as that player, I can't distinguish whether it's this point or this point or this point. For me, all of these points are the same. So either they are all a part of A or they are all not a part of A. Or more like either I know them all or I don't know them all. Knowing half of them changes the status. Then I know something more, which is not the scenario here.
So probably I missed something. Maybe because I got disconnected for a while. But can you explain this diagram? That so how I viewed it? Like say I understood that there is a partition and something occurred,
Okay.
and then we are looking for the occurrence of that event within the partition. And so I'm viewing it from the pluralistic viewpoint that yes, the event was there as
So
one of the
let
element
me
of.
let me explain this quickly. Let's say this orange region is the event A, What I've drawn in this light cyan color, it's the partitions for some player I. What I have in this dark green color, this one, these are the partitions for some player J. Now what I'm saying is, suppose let's focus on this point W. Now this W is a point which lies in a certain region, which is this this element of this capital Fi. So this is some Fi of omega.
And
All of these point,
what this Fi here is? Capital F.
it's an element of the partition.
Okay, okay, all right. Because partition is a set of the sets, right? So this Fi itself is a set. Is
Yes.
it like this?
Yes.
Okay. All right. And then,
Now any point here can't be distinguished from the other. A player does not know whether it's this point or this point or this point. Okay, so what we want is either all of this is a subset of A. If that happens, then we say that that particular omega is part of the knowledge operator. It belongs to Ki of A.
mhm.
On the other hand, consider this point. This point is in the region of A, but I can't distinguish this point from this point. And the region covered by these 2 points is not a subset of A.
And what's the
Meaning,
meaning of this statement when you say that I cannot distinguish this point from that point or the from other point?
so
What does it mean?
it's just like saying a colorblind person cannot distinguish between red and green.
Okay, okay, all right,
Yeah.
right.
So, because we can't distinguish between these 2 points, and we are ultimately bound to consider this whole region, which is fi of some w1, and this whole thing is not a subset of A. That's why this w1 or even this point cannot be a part of the knowledge operator. So this is the exact same thing that happened in the example that I gave.
Yes, and what are we trying to achieve by identifying the knowledge operators?
We're trying to, there are certain properties of knowledge operators, and we're trying to see what is known to what agent, what is known to whom. It's kind of like that. And if we can reach the point of being able to say, is there something that is common knowledge to all of them?
Okay. So does this mean that we are trying to establish a shared knowledge shared among the agents so that they can communicate with one another? In a sense,
There is no communication. This is
oh,
non-cooperative settings where communications are not possible.
okay, okay, all right.
Yeah. Okay, so now let's take this example. This is from class. Okay, to be able to take this example, you'll have to be able to see the partitions. Now, I want you to find out what is K of A for John and K of A for Paul, where A is given in the following way.
So for the John, since this A is this one, this entire A is there in the F of John is one of the partition.
Yep,
So this is going to be included into the knowledge, this knowledge stuff.
exactly.
Knowledge operator, right?
So Kj of A is just A. What about Kp of A?
So in this second thing, this SGB comma P is also one of the total partition. Is it a total one or not total one? Total partition, right?
Yeah,
So this will also become the part of the knowledge. But even
these
though
are
I could,
separate.
yeah, I could, yeah. Okay. This is the bigger one, right? So this is the partial stuff. So the KP of A would be equals to 5 then.
Huh?
Because it's CB, comma P and NCB, comma P, both are there in the partition. Yes, both are there. So yes, but though, even though, yeah, so I mean, these calculations could be correct, but it's still, I mean, the purpose of computing this KI is not that clear. What are we trying to achieve
Okay.
by
So
including this?
here we are trying to see what does agent John know about the event A, or what part of it is he aware about, and what does P or Paul know about some event A. That's what we are trying to establish here, and in different variations, that's what we are going to be doing. Now, okay, let me ask the next possible questions. Um, Now you can already see this. Kj of A turned out to be A, but even otherwise, Kj of A and Kp of A are some events. And what we are doing is we are looking at what is the knowledge or what player J knows about that event. So we can always ask this question: what does Paul know about John about the certain event A?
So, like in this case,
Actually,
so please,
sorry,
yeah,
let me
please.
interrupt you here. If you want to speak, please raise your hand. Or if you want to write, you can write in the chat box. That's completely open.
Yes, yes.
Okay, so now what about a situation like this where we are asking, does Paul know that John knows something about the event A? Or does Paul know that John knows the event A? So in this particular scenario, we know what this object is. This is just the event A. And we know that Paul knows about A. So what happened here is is in turn saying that Paul knows that John knows the event A. And we can similarly construct the opposite scenario also. And that will also turn out to be A. In fact, this means we can construct any order of them and we'd always know what that is, and that's just going to be the event itself. So it's going to be like Paul knows that John knows that Paul knows, and so on. So such a chain is possible, and when that happens, when such a chain is something that is possible, then we say that event A is common knowledge, meaning it is something that is known to both of them. It's not just that they both know the event, they know that the other one knows that event. A very simple example of a common knowledge is a news announcement that, let's say there were a group of 10 people who heard that announcement at the same time and they were paying attention and listening to it. So everybody in the group would know what the announcement was. They would know that all the other players heard that announcement. They would know that all the other players who know the announcement also know that this player actually heard that announcement. Meaning, it's like everybody knows that everybody knows that everybody knows, and so on. So, such an event is called as a common knowledge. And it's how these events or how the information is available to any particular player in the game changes a lot of things in the game, and that's the reason why we are going through the jugglery of doing all of this again and again. Clear?
Ma'am, I guess this common knowledge thing is quite clear now.
Okay, good. All right, let's take one more example. This was again from the class itself. So this is, let's say the event is NCB, comma red. So let's look at both of them. I'm saying NCB, comma red. What can you say about the knowledge of John for that event and knowledge of uh, Paul for that event? So the one that I'm referring to is this one and this one.
For John, I think NCBR and NCBG are completely equivalent because, for John, we know that he's completely colorblind,
Yes. So
and
for
for
him,
Paul, basically, uh, I think both partitions, because with Paul we don't know whether he's colorblind or not. So NCBR and
we don't know, but he knows. That's the main part. Because he knows, he'd know what state it is, whether it's NCB or CB.
okay, so if from his perspective, it is a second partition, but let's say if we don't know, then second and third partition both will be considered for Paul.
No, it'll exactly be this one. This is in itself a partition. So the knowledge operator for Paul for this event is that event itself. Because it's just one thing and it's partitioned as that one element itself. Or I can say that for Paul, for the event B, it actually is exactly equal to the event B. That is one particular partition. So this is like saying I'm talking about that particular element. Now what about John? For John, this particular event NCB, comma R, meaning Paul is not colorblind, but that's something he doesn't know. And the car is red. That is again something he doesn't know. So for John, actually these four form one club. All of these four are not included in B. That means the knowledge is 5. This is like saying John does not know if this event has occurred or not. Because he can't tell. He has a few different states and he can't distinguish between them. So from this point forward, we can't really say something very useful about things of this kind. We'll not get a common knowledge situation here, but we get something else. So this is going to be, right, I just placed the value of knowledge of that Paul knows B here, which is just B itself, and that is 5, which is like saying John doesn't know that Paul knows and we can do this in a few more different ways. We can ask the other kind of a questions. And this is by default 5 because knowledge of John about B is not existent. So Paul doesn't know because John himself doesn't know B. So the kind of questions that we are answering by dealing with these knowledge operators are, so it's like player A knows, player 1 knows whether player B knows about a certain event, or player A just knows about that event, or player knows about player 1 knows about player 2 that knows that player 3 knows a certain event, and so on. Like this can go on. So in this particular scenario, in the second case, because B is not something that is known to John, and hence John doesn't know that Paul actually knows B. So this becomes something that is not common knowledge. This is some knowledge that is available to John but not to Paul, or rather the other way around. So now let's take one last scenario. This is that the outcome is red, no matter what is the state for Paul. What can be said about if you want, you guys can answer in the text in the chat box itself. Okay, so in this scenario, when we are dealing with the case where the winning car is red, no matter what is the state of Paul, let's see what happens in the partition. If the winning car is red, that's fine, but John cannot distinguish between red and green. So this set is anyways bigger than C, so John doesn't know C. So this is phi. This is all right. Let's just focus on Paul for this case. For Paul, this is okay. He can see that this is one partition and this partition is a separate partition, and this is less than B. This is a subset of B, subset of C. So this is okay. But it's this object that he can't distinguish from this other state. So this will not be something that he knows. So this is a scenario when knowledge of a particular agent is less than C, and it's just he is not colorblind and the car is red. That's the knowledge. So this time it's not all of the event, it's just a part of that event. So again, C is not common knowledge here. In a slightly more formal way, common knowledge basically means or rather an event is said to be common knowledge in some state of the world for all agents if this kind of an operator consists of that W, that omega star. And this part just says player I1 knows that player I2 knows ... till player I1 IR knows A. So this is one player knows that the other player knows that the other player knows, and so on. That's the kind of scenario, and this is true for any particular order of them. You can change the order, you can have them come up more than one times. In that case, if in all of them a particular omega star exists, then such an event is said to be common knowledge in that event. Now, this knowledge operator has a few properties. Some of these properties you can think of in a fairly natural way just by making diagrams and thinking about it, and also you can prove them formally. So let me see if I can just make small diagrams to make my point. This first one, it's just saying that suppose this is partition for one player, and let's say this is the partition for the other player, and the event is, oh, okay, the event is this. Then the knowledge of operator of any of these, which is going to be for this second agent, player 2, it's just going to be this. This is K2 of A. For player 1, there is no K2. He doesn't know the whole of A. He doesn't know it. He can't distinguish certain things, so he doesn't know it. But whatever happens, this K2 of A or K1 of A, if it existed, it would have to be a subset of A. It can't be bigger than A itself. That's just from the definition. So that's one point that we can get from here. Next, if suppose we had not one but two events and we had a hierarchy in those two events, meaning we had an event A and B, both a subset of Y, and we knew that A is a subset of B. So let's say in that same diagram above, let me draw B as well. So let's say B is this. Okay, so B is that bigger portion. If that happens, the chances are the knowledge operator of B will include more things than what would be included in the knowledge operator of A. So the same hierarchy is preserved even at the level of knowledge operators. That's what this one means. Next, suppose we just have some event A, then if an agent knows that event A has occurred, that means he knows that that event has occurred. So this is a bit redundant in if you were to say it in English, but proving this requires you to use the previous two theorems and a little bit of more things from the definition itself. But all this is saying agent I knows the event A. This is saying that agent I knows that he knows the event A. Or this is like saying that he hasn't forgotten it. So this is a sensible thing if we are dealing with unlimited memory, or that the players are not absent-minded or forgetful. So in that case, this is a natural thing to expect from knowing something, that if they know something, they'll retain it. It will not go anywhere. Now, a few more properties of this operator are as follows. So if we were to take the knowledge operator, if we were to take the knowledge of the whole set of state of the world, meaning the whole Y, then that has to be the whole thing. So this is like saying we are taking this whole thing. The knowledge of that should give you the whole thing for all agents. And this is just saying that the agent knows that that is the state of the set of all the states of the world. Another property is, suppose we are dealing with one particular agent and we are saying what is the intersection of knowledge of A and knowledge of B. So we can look at that in this above example. In this example, I have a special structure between A and B, but nevertheless, this is the same as saying what is the knowledge operator of the event A intersection B. So here in this particular example, A intersection B is just A, which is why we would get this in the focus. Okay, now one more property is the following. This is a bit of notation, so this needs to be carefully understood. This notation means I'm talking about The complement is on the outside, which is saying that player I does not know A. That's not the same as saying player I knows the complement of A. These are different objects. This one, K of I of complement of A, this is the part that means that player I knows complement of A. Okay, the only relationship that we can have of this object with something similar is that if an agent doesn't know something, then he at least knows, he himself at least knows that he doesn't know that something. That's all this statement means. So this means um, the equality here means player Pi knows that player Pi does not know the event A. Yeah.
Actually, player I knows that does not know and know, that is a bit confusing.
Yeah, this is a part of the way it's defined. It gets a bit confusing. So the point that you need to focus on here is Ki of A. So if we were to think of it in a slightly diagrammatic way, say this is some kind of partition. This is my A. Okay, Ki of A would be this, if what I've drawn are the partitions for I. So Ki of A would be this component, this portion, this particular partition from the bigger partition, this set of it. The complement of it is the remaining portion, but in the remaining portion he doesn't know whether it's this portion or this portion or what. That's the meaning of this. Okay, on the other hand, this clearly is saying, for the same diagram, let's say I'm able to draw it. Assume that it's the same diagram. Okay, it doesn't look the same, but just for the sake of it. So this is event A, this is again event A. Ki of complement of A means that I'm not focusing on A at all. What I'm focusing on is this region. What I care about is this region. And I am interested in finding out what can be known here. In this particular scenario, there are no complete partitions, but if there was one present here, then this could be Ki of A complement. While when we were talking about that player I does not know the event A, that's just leaving all of it as it is. We're not able to say anything. This, he knows there is a particular A complement is just another event, and he's repeating all of that. That's still fair. Okay, good. So this is a few definitions. You should practice these. There tend to be good questions coming out of these definitions and trying to prove these properties. In fact, in certain problems you might be given given an event, and for that event, these are general properties obviously, but for a particular event something more might hold. So how can you find out the relationship between different ki operators? These are like very standard kind of things that can be asked. Okay, let me just quickly scan through what I have planned, because we've taken more time than we thought. Okay. Alright, so I have two questions here. These are just to sort of try and understand how to find or how to get to the state of the world, how to find the common knowledge in a particular scenario. I have two examples. I'll solve one of them and I'll leave one for you to try out later on your own. If you have any doubts, you can ask me next time. If we have a time at the end of the class today, I'll do that one also. Okay? So let's start. So this example is, we have two agents. There are total 8 state of the world, just numbers from 1 to 8. We're given what the partitions are. These are the partitions. So one is, if he knows if the true state is 1, he'll know. If the true state is 2, he'll be confused between 2 and 3, and similarly so on. And also we are given the state of the world for the other agent. Now if we want to find, so here we are told, okay, state of the world is, like the true state of the world is 2, then what is the common knowledge? And if the state of the world, the true state of the world is omega 1, then what can you say about common knowledge? So how do we find what is the common knowledge in a particular scenario? So one way of finding common knowledge would be to try and find an event for which this type of a property holds. But this, we know there are combinatorially a lot of different variations possible, and it's just infinite versions possible, so we can't do all of them. So in the lectures something was pointed out. Let me get to that point and skip a lot of the other things for the time being. Okay, let me go through the main theorems that will be useful to get the answer to this question, and then you can try coming up with the answer. So the two theorems that are useful here are the following. They're both related to common knowledge and something else. So let's go through these theorems. So this first theorem is saying, if event A is common knowledge in some state and the partition for player I for that particular state has other states also. So this is similar to our above example of colorblind and not colorblind and so on, where we had different partitions. So there could be partitions which had things more than just the true state of the world. They had some other things also. So let's say there is another such w dash, then the event A is said to be common knowledge in that other state also, or in that other w dash also. This was one thing. Another thing was to sort of try and capture the structure of common knowledge itself. So they said that, okay, let's think of this scenario in terms of a graph, where the edges of the graph, the vertices of the graph are the states of the world. So suppose if there are 3 states of the world, so it's W1, W2 and W3. These are the vertices of the graph. And the edges are the ones which for some agent, doesn't matter which agent, they are put together in one partition. Okay, if that happens, then there is an edge, otherwise there is no edge. So let's say in this example, the edge is between just W and 3, W2 and W3. What we get at the end of this, let's say this is the max connection that is possible, this is it, there are no more edges. Then what we have gotten is this component and this component are some connected components depending on which W we are talking about. So if we are talking about W1, this is the connected component, that's just one state of the world, nothing else. On the other hand, if we were talking about W3 or W2, so C of W3 or W2 would be this part, the connected component or the path connecting all of them. I've
Okay, so
taken
each component forms a partition, like a separate partition. Like this W3 and W2 will form a separate partition, and W1 will form a different partition.
let's not use the word partition again here, because partition means these Fi of W's.
Okay.
Try to remember this terminology. This is connected component.
Okay.
So in the graph, things that can be reached from one point to another via at least one connection, one path, that's what is connected component of that graph, when we are referring to that one vertex. That vertex is mentioned, one of those vertex is mentioned. Okay, so this is one possibility. Another could have been this also. In that case, all these three together are forming a connected component. Now, this is what is very useful. This next theorem says an event is common knowledge in some W star if that event is a superset of the connected component. Or since this is a if and only if situation, if there is an event which is a superset of the connected components, that forms, then that event A is common knowledge in W star. And this is exactly what we're trying to use. This is what we're exactly going to be using now. So let's find out the connected components for the W that we are given. We are given the partitions, we are given what W to focus on, we are given what they're calling as W star. All we have to do is create this connected graph. Once we have that connected graph, we'll be able to say something about at least one event that is common knowledge for that given W. Okay, so the idea is to focus on creating the connected graph, and creating the connected graph is easier than trying to do it using the definition like from scratch. So let me rewrite this here. The graph is y comma e, where this W and W dash form one particular E if W dash belongs to the partition for any A. Okay, so this so we know how to create the graph, and all the things that are going to be connected to each other will be one part of it. So let's try doing that for this example. So we have 1 2 3 1 2 8, right? We have 8 also. Okay. Okay. Actually, we don't have to think too carefully about it. from the beginning itself, we can see 1 is something that's not going to be a part of the connected component, so we don't have to worry about it too much. But let's focus on the other ones. So we are told W is equal to 2. We're starting with 2. So 2 is connected to 3. This is for agent 1. This is what I'm using. They're connected when along with 2 there is some other state of the world that lies in that particular partition for any given agent, either agent 1 or agent 2. So for agent 1 we see 2 is related with 3. For agent 2 we see 2 is related to 5 also. So in the bracket I am writing based on which agent did we come up with this edge, and the edge just refers to this exact connection, that these two can't be distinguished. So this means 2 and 3 can't be distinguished according to 1, 2 and 5 can't be distinguished according to agent 2. Now this is done. Oops. This is done. This is done. These two are done. Let's look at the next step. So from 3, is there something 3 is connected with? In both the scenarios.
No, 3 is like a separate thing.
3 is like a separate thing. Never mind. So we don't have to worry about it. Now, from 5, is there something? From 5, we have a connection to
Yes,
4.
4.
This is for agent 1. And then, okay, maybe this was not a good idea. 6, 7, 8. Now, according to, so this is something that I've used. This is the next part that I'm using. According to agent 2, 4 and 6 are connected, and that these two can't be distinguished, and also 4 and
7
can't be distinguished. In fact, this also means 6 and 7 can't be distinguished, but nevertheless that's not so important. And that's about it. Right? So what this means is, so what we've managed to find is, this is the connected component, connected component C for the state of the world W equal to 2. This portion, or if we were to write it, I would write it this way. It's 2, 3, 4, 5, 6 and 7. And from the proof of that theorem, we know that this is going to be common knowledge in W equal to 2. So for a particular scenario, we know what is common knowledge. And we managed to create this just based on the partition information and the idea that this can be interpreted in the form of a graph, where the edges of the graph refer to whether two of those states of the world can be distinguished from each other for any player. Okay. Next, is what is connected component for 1. There's no connected component for 1, it's just 1 itself. So this will form a common knowledge in the state W equal to 1. Okay, so it's like saying this is the minimum. Now what if I say, suppose there is a state A which is 2, 3, 4, 5, 6, 7 and 8. I forgot 7. Can I say something about this state? Can I say something about this event? Sorry, not state. Is this common knowledge for W equal to 1? Is this common knowledge for W equal to 2? Or both? Or neither? So see, the theorem was a if and only if condition. That's point number one. If an event is common knowledge in this, if and only if A is a superset or equal to CW or the connected component. So this is definitely true if we go in the backward direction also, which means if there is an event A which is a superset of CW, then that A should be, that event should be common knowledge in W star as well. Okay, this should have been W star, by the way. So this tells us that this event A, which is clearly a superset of C2, this should also be common knowledge in W equal to 2 state. And then we can come up with more events and check if that is common knowledge for a particular scenario or not by just repeating this process. So there's one more example. If you want, you can try it out. Oh, this example does not talk about common knowledge, because I think this example doesn't have common knowledge. A and B are at least not common knowledge. You can use the method of connected components to verify. Okay, let's try this out. Doesn't look that difficult. Okay, so this is so the first one is the event is given as 1. The state of the world are from 1 to 8, and we are given the partition of both the players. So K1 of A is just looking at the partition that contains 1. So the partition that contains 1 is this one. This is just 1 itself, nothing else. It can't confuse 1 with something else. So this is A. This is sorted, no problem here. Now what is K2 of K1 of A? So K2 of K1 of A, which we know is A, is just this. And now what is this going to be looking at? The component or the partition of the second player that contains 1. But this partition that contains 1 for the second agent is bigger than A. And by the definition, if it is bigger than A, then the player doesn't know. Fine? Okay, now this is like a whole sequence. So let's go one by one through this. K1 of B. K1 of B contains things starting from 1 all the way till 6. Okay, and since we are supposed to look at the partition of player 1, so we are going to be focusing here. So let's look at each one of them one by one. So if we are focusing on 1, then that's just one partition, so that's fine. So it can include 1, that's okay. What about 2 and 3? It can include 2 and 3 because 2 and 3 is a subset of B. So 2 and 3 is also fine. Now what about 4 and 5 or just 4? This is also okay because this is again a subset. So 4 and 5 is also fine. And lastly 6. Here it's 6, but here it's 6 and 7. We can't this player can't distinguish between 6 and 7, meaning now B is not a superset of this partition because 7 is not contained. So 6 also cannot be included here, that he can't know 6. So what player 1 knows about B is these states starting from 1 till 5. Next is we can repeat this for player 2, but only this time considering k1 of B as our event. So what will we get if we do this? Now we're supposed to look at the partition of player 2. So player 2, 1 and 2 is definitely a subset of B. Okay, we're not supposed to focus on B, sorry, we're supposed to focus on this. 1 and 2 is a subset of this, so it is fine. 3 and 4 is also a subset of this, so that is also okay. Now here 5 and 6 come together, they can't be distinguished from one another. But here 6 is not included, which means K2 will know about K1, that it knows about B, only this many things. It will not know all of B. So every time a player tries to know something about what the other one knows, the information is reducing. We can continue doing this. So next would be K1 of K2 of K1 of B. If you do this, you will get this is just 1, 2, 3. Same logic. 1 is fine. 2, 3 is a subset of 1, 2, 3, 4. So that's also fine. But 4 can't be included because 4 can't be distinguished from 5, and 5 is not included here. If you want, you can repeat the same process and get this as well. And you can check this turns out to be 1, 2, 3. Okay, any doubts so far? It feels like we have covered a lot of things, but we've mostly just talked about the knowledge operator and a couple of questions related to that. Okay, I have included small proofs of these, I think. Okay, yeah, these proofs were actually covered in tutorials also, so I'm not gonna go through them. If you want, you can go through these at a later time. These are the properties of the knowledge operator. We already talked about these two theorems. These two theorems are saying that these two theorems are basically talking about common knowledge, that if an event is common knowledge in a particular state W star, and if that W star is connected to some W dash, then A is also going to be common knowledge for that W dash, which is fair. Now, if we think of all of these things in terms of a graph where the vertices are the state of the world and edges are between W and W dash, such that the partition of W includes the other state W dash as well, that's when we create a edge, and this can be for any player in the scenario. There is no edge if there doesn't exist such a player. So at the end of that, whatever connected component we get, connected component basically refers to we can go from one portion of that to any other portion, and that there exists a path that we can take. Also, the way this is defined, it's also assumed that this is the maximal connected component, meaning okay, so could have been possible that I can say that okay, this is one connected component, but actually this edge was connected to a few more things. This could have been labeled as CW, but we are saying if an edge is connected we are including it in the definition of the connected component. If something that is not in C and is not connected, then that is not to be included in CW or the connected component. So point being, CW refers to whatever are the connections, all of them, and there might be other ones. This might be for some other, so this is CW, let's say, where this edge is W, and let's say this edge is W1, so this is CW1, something like that. So this next theorem says that an event A is common knowledge in W star if and only if it is a superset of the connected components for that W star. That means the forward and backward both are true, and it's the backward that we just used to try and find out a few examples of events which can be common knowledge for a given W star. Okay, now let's go through this another possibility. So here in this model, we have only talked about whether a player knows an event has happened, or whether a player knows that some other player knows that some other player knows, and so on, so on, so on, that an event has happened. Another way of talking about these types of models in a slightly more general way is to include probabilities in the mix. And the probabilities are some common probabilities, more like common priors, on the information itself. So all the agents would know that what is the probability of getting each of those W's. So in the previous example, we had 7 or 8 values for W's, right? Here 7 values, right? 8 values, okay. So if there is a probability assigned to all of them, and the sum of those probabilities ends up being 1, and each probability is greater than 0, so like standard definitions of probability, then that kind of a model is what we call as a model with belief. So apart from these things, there's a added component which is the probability for each W, and this probability is common for both the agents. Like it's a common prior, it's known to both the players, player 1 and player 2, or whatever is the number of players. So before we go to this theorem, let's take a couple of examples of Aumann model with belief. This is example from the text, from the lectures itself. So we can change the numbers if that would help you get an idea. Okay, maybe let's just do that. Okay. What are we left with? This is 3 by 8. Okay, so these probabilities are common and they're known to both the agents. So the situation here is we are told what is the partition, and the partitions are this way. So first I'm drawing the partitions for player 1. So for player 1, he cannot distinguish between 1 and 2, and he cannot distinguish between 3 and 4. The other partition is for the second player, and he cannot distinguish between 1 and 3 and 2 and 4. Okay, let's say to talk about beliefs or to talk about updates, we are focusing on Bayesian updates. So what we are asking is, given the information, what is the probability that a certain state is observed? These are the probabilities of them coming into picture altogether. Each agent will look at the information in a slightly different way because they have their own partitions in their information. And then finally, we are asking what is their belief about all the states of the world. So, if we are talking about, let's say, agent 1, then the information for him is partitioned in this form. And it just means that he can't distinguish between 1 and 2 or 3 and 4. So, that's the information for him. Either he'll be getting 1 and 2 or he'll be getting 3 and 4. So he'll be asking what is the probability of getting any of these WK given he has seen any one of that information. So let's say 1 and 2. Okay, that's the posterior update here. So let's do that. So this refers to the probability of WK intersection with whatever is the information. So in this case, the information is W1, W2, and this is to be divided by probability of that information, which can be just written as a sum. So it's just the probability of W1 and probability of W2 and whichever K we are talking about. So if K is 3 and 4, there's no intersection. So these two are just going to be by default 0. So let's take this to be just the probability of WK in that case. So K is in this case either 1 or 2. So probability of 1 and 2 is 1/8 and 1/4. So let's say if it's K equal to 1. So that's just 1/3 and 2/3. Okay. So this is 1/3. This is 2/3. Okay. We can repeat the same process, but next time the information would be 3 and 4, and hence these two would just be 0, and only these two will remain. So in that case, we'd get would be.
So, ma'am, in simple words, like the beliefs are updated based on real world experience. So, can we just say that in this case?
Okay, so it depends what kind of real world experience you're talking about. What is the process of talking about real world experience? You have to say what
events,
process.
like the event that we are observing here. So, these events will update the probabilities, which means like which are beliefs in simple sense.
But we are doing a Bayesian update. There are a few other ways of doing these updates that are not common but that are there. For example, maximum likelihood and so on.
MLE, yeah.
MLE, yeah. So as long as we have this update rule, whatever that update rule is, whether it's MLE or Bayesian, that's just telling us that this is how the update is happening, and then they're just calculating those probabilities. So in this case, 3 and 4 are 1/4 and 3/8. Very bad values. I think this is 3/5 and this is 2/5. This is for k equal to 3 and this is for k equal to 4. So what I have done here is, this is the posterior belief of agent 1 given the information. Now, if we are told that the true state of the world, right now what I did is, no matter what is the true state of the world, we have created a whole table and we have the whole belief set available. The whole thing is available to us. If we are told what is the state of the world, let's say we are told it's W1. True state is, then all I need to care about is this one. And this is only for player 1. Similarly, we'd repeat it for player 2 as well, and we'd create such a belief table, which would be the info. The info is 1 is related with 3 and 2 is related with 4, as in these two can't be distinguished. And we'd have the posterior belief of player 2 as well. Same process, we just have to repeat, we have to do those calculations again. So it's WK given whatever is the information. Okay. Now, right, any doubts so far?
Don't think so, ma'am. I think things were quite clear with this. If there is any doubt with the issues as well.
Sorry, are you saying no doubts here? So let's continue.
Let's continue, ma'am. No doubts. No doubts.
Okay, so I'll skip going through more details for this one then. Okay, at last I have one more example, so let's take that. Okay, so now this is again something similar. We are given some states of the world, we are given some partitions. Now there are more states, that's the only difference here. We are told what is the true state of the world and we're supposed to calculate first order belief. So the same thing, we're supposed to repeat that, but we're told certain things here. So let's calculate the whole thing. So let's say we are asked for player 1, right? So to be more specific, what they exactly are asking is, for player 1, calculate when W is equal to 7. What is the first order belief of that W is equal to 7 when the true state is this, meaning we are in this information set. what is the probability of this? That's what we are being asked to calculate. That's quite straightforward. That's just the probability of W being 7 divided by the probability of the state 7 and 8 both. So that's just 1/8 divided by okay. So this question was asking us what we have calculated in the previous one, but this is in words, and we are calculating the first order belief.
Man, the events in Y are equal likely, like they all have same probabilities if it is not mentioned otherwise.
It will be mentioned. If it is not mentioned, you'll have to ask. It
Okay.
may have been missed. Right now, it's given that they're equal.
Okay, they're equal.
In the previous question, we had them different. We had these strange values.
But like if it is not given, then can we assume it is like equal likely?
No.
Like so it will be given, right?
It has to be given. Because if it is a model with belief, you need those belief values. You need the common priors. Otherwise, everything changes.
Okay, thanks, man.
Yeah. All right. So, okay. So, we could calculate other things here. For example, what is the probability? I'm just pointing out a few of them, not all of them. For example, what is the probability of W being 5? Okay, this is for player 1. In the same state of the world. So if the state of the world is 8, true state of the world is 8, then what should be the probability of this?
So we are given 5 if we know that 8 has occurred.
Yes.
So it should be 0, I think.
Exactly. It should be 0 for the reason the information is actually 7 and 8, and there's no overlap between 5 and 7 and 8, right? Because the event that has occurred is focused on this information set, and hence it can't focus on anything else. So this is going to be 0. Now let's just try out for the other agent as well. So let's say same question for player 2. What is the probability of getting W equal to 7 when the state of the world is 8, whatever information set that refers to? What will this be? Just as using the same arguments as before, now we're talking about player 2. So for player 2, if the state of the world is 8, that's actually going to be known because it's separate from everything else. So the probability of getting 7 is going to be 0. And similarly, the probability of getting anything else is going to be 0 because the probability of getting 8 is going to be just 1. So this is just 0. Let's say instead of that, if I'm saying the state of the world is this time, sorry, if let's say the state of the world is 7, then what happens?
I guess the probability will be 1 by 3.
Exactly. The probability is 1 by 3. Okay, so you've actually managed to understand this quite carefully. So good. Is it clear to others also? The next thing, like the next level of generalization to these Aumann models with belief would be without common prior, meaning these probabilities would be different for different agents. Like player 1 would think the probability of state being 1 is say 1/3, the other would think maybe it's just 1 by 8, something like that. So once it starts differing, that is similar kind of a model but more involved and more general. So now this is the next question. If the state of the world is 8, calculate the probability player 1 ascribes to event A so it's still the same thing. We are going to look at the intersection of A with whatever information set is created by W star being 8 and do this. Okay, so let's look at A. A is this 1, 5 and 8. A is chosen in a very smart manner. So with A being 1, 5, 8 and F1 of 8 being 7 and 8, we just get that we're looking at the probability of 8 for the even probability of 7 and 8. That's just half. So the probability that is given by player A to event A for the true state being 8 turns out to be half. You can try it out for, let's say, the scenario where the true state is is 4. Again, for the same player. So for player 1, it's 4, 5, 6. That's the information set. And the intersection is with 1, 5, 8. That gives us the probability. That's just 1/3. Everything has probability 1/8, so the conditional probability would just be 1/3. And we can repeat this process for others. We can try it for player 2 and see if what happens here. For player 2, the information set containing 8 is just 8 itself. There is no partitioning. It can be distinguished, it can be known. So this is just probability of event 1, 5, 8 intersection with it's just 1.
It will be Z is okay 1.
1. Maybe we can try something different. We can try the previous one. If the true state of the world is 4, we don't know what comes here. That's the one that's going to decide it all. When the true state is 4 for agent 2, this is the partition that is to be considered: 1, 2, 3, 4. Okay, so this becomes
Should be 1 by 4.
exactly. So in this example, you can see that the probability that a player ascribes to some event is actually different for different agents for the same event. There are quite a lot of differences. This is what you would expect in general. But there is a very interesting theorem which says, so there are conditions in this theorem. So let's say we are talking about a special case with just two agents and A is some event. If the probability ascribed to some event A, let's say that value is W1, is common knowledge in some state of the world W, and similarly P2, which is ascribed to the event A and the value of that probability is Q2, that is also common knowledge in that same state of the world, then P1 and P2 have to be equal. This is a kind of an agreement theorem, which is saying, I think it's called also Aumann's agreement theorem. And what this theorem is saying is, if these types of probabilities that we just calculated, this probability or this probability, if they formed, or if we were to write them slightly more carefully, so like all the W's for which, let's say PA of some information, so let's say F1 of W, so I'm talking about only one agent for the time being, let's say, or maybe I, okay, is equal to some value, okay, some value Q1. If this guy is a common knowledge, and similarly for the other player, so this is set C1, this is set C2. So that theorem is saying that if these two things, if C1 and C2 are common knowledge, they're common knowledge in the event W, that basically tells them that Q1 and Q2 has to be the same thing. Which is like saying, if people started out with the same belief, if the two agents started out with the same belief, and then these types of probabilities or these types of events, where they're looking at the probability ascribed to some event A for with the first order belief for agent 1 and agent 2, and the process of update is similar, meaning that they've used, for example, Bayesian update rules, for example the ones that we saw here, or any other, but some rules that are known to everybody, and that these events are known to be common knowledge. If that happens, then these beliefs have to match. Note, we are never saying that they have to match if they have the same information structure. If they have the same information structure to begin with, same prior, same update rules, they should get the same update values. But what we are actually saying is their update rules are similar. They're starting with the same prior, but their information partitions, for example, in this example, here, the information partition could be different, but it's still in such a way that these two objects, okay, this is still about the theorem. These two objects are common knowledge. If that happens, then the output has to match. Or in other words, if you were to think of it in a reverse manner, then it's saying the only situation where the outputs, the update outputs or the beliefs will not match is if one, they either started with different priors, meaning both agents started with some different priors about a state of the world. That's one possibility. Another possibility is that their state of the world, their these types of events, C1 and C2, the probability is ascribed for any event given the information or the first level belief. Those are not common knowledge. Something is different there. They're interpreting it in a different manner. And that's the only scenario when Q1 and Q2 will not match. That is, the belief will not be exactly the same. So, with this, we have covered all the things from this week's tutorials and the lectures. Yeah, any doubts? Okay, I'll quickly recap because I think it feels like we've covered a lot of things. So, okay, so today we mostly talked about the knowledge operator. The best way to think about knowledge operators is in terms of this diagram, where what I've drawn is this outer circle. This outer circle refers to all the state of the world, or Y, and I have made some partitions. The partitions color wise refer to different players. So, knowledge operator basically says it contains that particular region which can't be distinguished by their measurement or their sensors. So, that together is what is contained in Ki of A if that is a subset of the event A itself. So, for example, this is the one that lies inside of the orange region. So, this is one possibility. Or this one for the other agent. Meaning the two agents can have different knowledge about the same event. They can know only certain parts of it. They may not know the whole thing. So, we saw a few examples of that. And we saw in what cases we can get common knowledge out of it. Common knowledge is the scenario where player 1 or player 1 knows that player 2 knows that player 3 knows, and so on, the event A. And all of this can be in any different order, so this goes on till infinity. If that state of the world W star lies in this knowledge operator, then that's what we say that event A is common knowledge. This common knowledge operator has a few properties. Then we saw, suppose we are given a simple scenario with some players, state of the world, the set of state of the world and their partitions, and we are told, okay, for this state of the world, what is a possible common knowledge? What is the possible event that can be a common knowledge? So we found one such example. What we did is we just found the connected components for W equal to 2. That's the maximal connected component rather. And then if A is a superset of that, then that's superset of that, or in fact it can be even equal to the connected components, then that is going to be common knowledge in that state. And we repeated that for another scenario, and we saw a few more examples that are around calculating these knowledge operators itself. And lastly, we saw some theorems related to common knowledge. Theorem 1 is saying if we have state of the world W star and W hat that can't be distinguished by some player, and that the event A is common knowledge in W star, then that event A has to be common knowledge in that W dash as well, which is some state that cannot be distinguished by some player I. Now, another way of looking at common knowledge is to think of it like a graph where the vertices are the state of the world and edges represent if two states cannot be distinguished from each other by any agent. So it's this scenario. In that case, what we get formed, the whole path that we get formed of connected components is termed as CW. So an event that is common knowledge in some state of the world W star, an event is common knowledge in some state W star if and only if A star, if A is a superset of the connected component. And since it's a if and only if condition, it holds backwards also. And then at the end, we saw the Aumann model with beliefs. We saw a couple of simple examples of that. And we finally saw the agreement theorem, which tells us if two agents are starting with the same prior and their probabilities ascribed to an event A are common knowledge, the values may be, let's say, Q1, Q2, then those Q1, Q2 values necessarily have to match. And this is just some examples related to belief. Yeah. Okay. Anyone has any doubts here? Okay, then we can end the session. Thank you for joining. Bye bye.
Yeah, thank you so much. Bye.